Well, welcome to another lecture for Introduction to Computer Graphics. For today's lecture, we're going to be talking about textures. So what are textures? Well, let me see. Let me try to give you a definition of what textures are. Textures are the ways with which we define information for objects. I think this is a comprehensive definition. Let me expand on that just a little bit. There are the way by which we define information on objects that are not necessarily connected to how the objects are defined. So, not a very useful definition of what textures are, because I'm trying to be comprehensive, and textures are used in all sorts of places for all sorts of different types of objects. I didn't say surfaces, right? There could be surfaces, there could be other types of objects. And we have different ways of specifying textures. You may think about some very specific things in your minds, but there are various ways of specifying textures. And also they are used for numerous purposes. There is not just one thing we want to do with texture. There are many things that we want to do with textures. So this comprehensive definition is not very helpful. So what I'm going to try to do today is that I'm going to start with a very narrow definition of what a texture is. We're going to keep it narrow, and then we're going to expand on this a little bit. Actually, we're going to continue to expand on the definition of textures as we start talking about other things in computer graphics. So by the end of today's lecture, we're not going to have a comprehensive definition of texture. And by the end of next lecture also, we're not going to have a very comprehensive definition of texture. We're going to expand on this a little bit. So we're starting narrow, but I want you to understand, as we start narrow, that textures have a wide range of uses. And when you say texture, people may think about something very limited, but actually it means a lot of different things in computer graphics. If you go beyond computer graphics, textures can also mean a lot of things that don't quite fit in the definition of textures that we use in computer graphics. But never mind about that. We're limited to computer graphics, and the narrow definition that I'm going to talk about is that a texture is going to be an image. An image that we're going to put on a surface, or a model, right? That's all we're going to do. Just a very narrow definition of a texture. We take an image, we put it on an object, we put it on a surface. And so if I take this texture and put it on this lovely teapot, the lovely Utah teapot, what I'm going to get is this guy. Alright, I mean, why would you put bricks on a teapot? I don't know. Actually, there's a very good reason for that. When I was teaching ray tracing for the first time, when I used Utah teapot, then I had a brick texture, so I just put it on it because I didn't really have much time to think about it. It's been many years, I'm still using this texture on it, so that's the reason why. But never mind about that. This was an image, I put it on my surface. Right? This is texture, right? Now, the immediate question here is, alright, the immediate question is probably why brick on a teapot, but I explained that. But the next question is, how do I do this, right? How do I take this image and put it on a teapot? I need to figure out a way of taking that image and put it on this model, right? All right, so let's talk about a few ways of doing this. I can just linearly map it like a planar mapping. Well, I guess I should do it this way, right? I take that image and just flatten it on the surface. Well, it's already flat, but I just push it on the surface of the model. So it would look like this. I mean, I could define a function to do this fairly easily, right? It's not too hard, but I'm not getting there just yet. So that's one thing I could do. I could do something just a bit more complicated, like, try to map this from every direction. I could just put this texture on the surface from every direction. So that could be like a cubicle mapping is what we call. I could try to wrap it around this in like a cylindrical way, and maybe cap it on either side. That's another thing I could do. Or I could do something like this, like a spherical mapping. Does this look familiar? It should look familiar. This is a representation of the planet that we're living in. When you look at maps, most maps use this sort of spherical mapping. So the funny thing that happens here is that, well, actually, they don't use exactly this, but they, a version of this. So the funny thing that happens here is that if you look at the top edge of this map, the whole top edge turns out to be just one point on the surface. So I collapse that entire edge up here, the entire top edge, onto one point at the North Pole, and the bottom edge becomes another one point at the South Pole down here. So this is not so great because, hey, I'm gonna have a lot of pixels to define this top portion of my texture here, which is going to map onto a very small area on that surface. But if you look at the equator here, like the center of my texture, it's going to be mapped around the equator, so it's going to be mapped around a large area. So the texture is going to get distorted quite a bit, right? So yeah, when you look at the world maps, what you see on the map is quite distorted. It's not a very good representative of what actually is on the globe, right? And the same thing would happen with this kind of a mapping. But for a lot of purposes, this could be a preferred way of taking a texture and putting it on. It's like a spherical object. Here's another one. This is called, I believe, shrink wrap. So you take this texture and you just wrap it around such that the entire perimeter of the texture, all of the edges and the corners, they all come down to this single one point over here. They all collapse onto one point. So you can wrap it that way. All right, so these are different ways of just taking a texture image and putting it on a surface, but these seem like very simple functions, right? Or relatively, even this one is not a very complicated function. This works fine if I'm trying to map something on a sphere. It's okay, but what if I have a dinosaur? What do I do then? Things get a lot more complicated, right? And things are a lot more complicated. So we're going to have to figure out a way to represent very complicated functions of taking this image and putting on the surface of our model. And we're going to do that using what we call texture mapping, sometimes called UV mapping. So let's talk about texture mapping. Let me start by saying that texture mapping is horrible. It has so many problems. I can go on and talk about this for a very long time, but this is the main method we use for defining textures on surfaces. So it's important that you understand this. Texture mapping. All right, so here's the thing. The problem with texture mapping is to define a function that will take my texture and map it on an object. So it's a mapping from between the object space and texture space. Now, oftentimes, this is how people think about texture mapping. Like you take a texture and you map it on the surface. That's not actually the correct way of thinking about it. The correct way of thinking about it is going to be the exact opposite of this. So what we're going to map is that we're going to take our object and map our object onto the texture space. So that's what texture mapping does. It goes in the opposite direction. And the way we're going to do that is, well, since we're using polygonal models for representing our objects, which are eventually converted to triangular meshes, right? So let's think about triangles and let's talk about this in the context of triangles. So my object is basically a collection of triangles. So to be able to define a general complicated mapping is that I just need to know where the triangle lands on the texture space, right? So I just need to know the corresponding position of that triangle in texture space. And that's going to define my mapping function. So this is not a mathematical way of defining this mapping. And so we talked about spherical mapping or cubical mapping or cylindrical mapping. This is not any of those. Actually, I don't necessarily know exactly how this mapping was defined. All I know is that my triangle here, this one triangle, maps onto this particular point over here. So this sort of abstracts the function that I use for creating this mapping from how this mapping is stored. For defining this mapping, all I got to do is for each one of my vertices, let's say for this red vertex over here, I need to know where it lands on the texture space, right? Its corresponding position on texture space. Same goes for this green vertex. I need to know where it is over here, and for blue vertex, I need to know where it is in texture space. And if I know all that, then I am pretty much done. And of course, this is going to define a mapping from our object space to our texture space. My texture space is going to be defined, of course, by it's 2D, right? So I'm going to have an origin, and I need to pick two directions. So for origin, we pick the bottom left corner. I mean, it could be top left. That could make sense. In some ways, it does make sense. But we typically pick the bottom left corner as our origin. And then I'm going to name two directions. One of them is going to be U, the other one is going to be V. And that's the reason why we sometimes call texture mapping UV mapping. Basically, taking any point in object space and putting it on this UV space. I'll say more about this UV space. This image looks like a good mental model of what's going on, but it's there's something minor that's not really correct. So we'll get to that later, much later. For the time being, this is good enough. All right. So for any position in my object space that has XYZ coordinates, if I'm working in 3D, obviously, I'm going to have a corresponding UV coordinates in texture space, right? So that's the whole idea behind texture mapping. And again, what's important here is that I'm not defining a complicated function. I'm not defining a spherical mapping or shrink wrap mapping or whatever cylindrical mapping. I'm not defining anything. I'm just taking every triangle and I'm directly mapping it in texture space. Okay, I mean, this sounds fairly nice if this mapping is given to you, right? It's very nice if I know the UV coordinate over here of each one of my vertices. That sounds like a very nice solution. But here's the thing, and the reason why I said that I don't like texture mapping. Somebody has to define this, right? Somebody's going to have to prepare this model and sort of define where each one of these vertices would go in texture space. Now, that's where the horror of texture mapping is. Because if I'm going to take every triangle and map it on my texture space and just manually move my vertices around in texture space, that's going to be quite labor intensive, to say the least, right? So we have some automatic methods for preparing this mapping, but they're mostly like semi-automatic methods. They don't fully work, but they work to a certain extent, and then people have to go and modify them. There's a lot of manual labor involved in this. This is a messy process. And in the end, you get all sorts of problems when you're using texture mapping for rendering anyway. So it's a very imperfect process, but this is typically what we use in computer graphics for mapping textures on surfaces. That's how we define textures on surfaces typically. All right. So yeah, I mean, get used to it and get used to dealing with the issues that comes along with it. But luckily, hopefully, you will not be the guys who will be defining this mapping, right? That you're going to just download some model and it will come with this mapping, and you won't even need to know how this mapping was defined, because every vertex will have a corresponding texture coordinate and you'll be done. I see a question. Do you think there will ever be a better process? There already is a better process. I'll get to that. I'll get to that at the end of this lecture. All right. But let's talk about how things fit in our GPU rendering pipeline. So this was our GPU pipeline. Remember, we're feeding in triangles on one side. They go through our vertex shader. Actually, each vertex goes through our vertex shader. And then we form our triangle primitives here and send them to a rasterizer. Rasterizer forms our fragments. And then we call the fragment shader to define the color of each one of our fragments. And finally, we get this lovely image. All good? All right. So where does the texture fit in? Well, we're going to need this texture when we're defining the color of the fragment, right? So a natural place to put this texture would be, well, it can't come along with triangles. So I'm going to have to feed it in separately. That's what I'm going to do. I'm going to feed my texture separately and send it to my fragment shader and say this is my texture, right? So what's going to happen is that as I'm passing my vertex positions through my vertex shader as one of my vertex attributes, I am going to be passing the texture coordinates as well. So one of my vertex attributes is going to have to be my texture coordinates. So if I have those texture coordinates, I can just pass it along to my rasterizer, and then my rasterizer can pass it along to my fragment shader, and then I can use that to figure out what the color is at the corresponding position for my texture. So here's how that works. My rasterizer is going to create these lovely fragments, right? And it's going to have to compute the corresponding texture coordinates for these fragments. Now, these fragments over here, they look like little squares. Like, what's the texture coordinate for a square? I can't do that. It makes no sense. So we're going to look at the centers of these fragments. All right. So my GPU is going to compute the corresponding texture coordinates for the centers of each one of these fragments. Centers of each one of these pixels, if you will. So let's take a look at one of them. So let's pick one in the middle over here. So how do I compute the corresponding texture coordinate for this point on this triangle? Well, it's fairly easy. We did stuff like this, right? Remember when we were talking about triangular meshes? So if I know, for example, let's talk about the position, the 3D position at this point. If I know the positions of these three vertices, let's call them P0, P1, P2, and let's say the position in the middle is P, then I can just do a barycentric interpolation. Remember the barycentric coordinates? I do a barycentric interpolation, I found this position. I can do the same thing. Well, we talked about doing this for color. I can do the same thing for the texture coordinates. So if my texture coordinates are like 2D vectors, U0, U1, U2, and I want to find U over here at this point, I just need to do this barycentric interpolation using my barycentric coordinates. There it is. Right? So we did this. We talked about how to do this. We talked about how to compute the barycentric coordinates. When we're rendering using the GPU, we won't have to worry about it too much because the GPU is going to do this automatically for us. Either the GPU hardware is going to do this or the software that runs on the GPU will do that automatically for us. We won't have to worry about this. At the end of the day, in our fragment shader, we will be getting the texture coordinate for this position automatically if we just define the texture coordinate for our three vertices. Okay? Simple enough. And if I know the texture coordinate for this little dots in this texture space, then all I gotta do is to just look up what color that texture is exactly at that point. Simple enough, right? I mean, at that point, I'm pretty much done, right? I know that point. So all I need to do is to look up that value in my texture definition, and I'm done. Simple, you would think. No. Our troubles begin there. We're just beginning. It was easy up until this point. Now things are gonna get a little nasty. So, sorry. Get ready for it. So now we're talking about texture sampling or texture filtering. That is the process of computing some color from a texture. All right, so I know what point I need the color value or texture value more generally. But let's talk about how to get that value out of our texture, right? So let's say that this is our texture, right? This is the texture is made up, well, it's a low resolution texture. It's made out of a whole bunch of pixels. But remember, we talked about this. Pixels are not little squares, right? Pixels are not little squares. They're more like values at a certain point on this space. And it's important to think about them, especially in the context of texture mapping like this. These are just points, values at certain points on this space. Actually, these are not even pixels. These are more appropriately called texels. These are texture elements instead of picture elements. Yeah, big difference. Yeah, I mean, for 2D textures, texels are sort of pixels, but we call them texels. All right, so here's my set of texels, and let's say I want the value at a point somewhere in this space. Like, let's say like this point over here. I want to know the value of this texture at that point. How am I going to do that? Well, the simplest thing I can do is to look at that point and find the nearest point, find the nearest texture sample, and just read its value. So this is the color that's closest to this point, color position that's closest to this point. I'm just going to take that value and use that. Simple enough, right? That's really the simplest thing I can do. Well, wait, when I do this, it kind of looks like I split this whole space into this grid, and it kind of looks like, yeah, I have like little squares for pixels now, for texels, right? So we sort of went to this definition of texels being little squares. But as I said, that's not what we're doing. That's not what we're doing. We're just saying that, we're in this space and we're picking the closest value. Okay, we're picking the closest value that's defined at this point in this case. Now, this is the simplest thing I can do, not necessarily the best thing I can do. I can do a little better. Instead of just looking at this one value, I can look at the closest values and do sort of like an interpolation of them. The closest values, in this case, would be these 4 values, right? And I can just linearly interpolate them to find the value at this point. And I don't call this linear interpolation because it's linear interpolation in 2 dimensions, right? So I'm going to call this bilinear interpolation. So it's basically a combination of 2 linear interpolation, or this sort of sampling the texture will be called bilinear filtering. So bilinear filtering is not a very complicated thing. I'm actually going to show you the equation and all. Not as simple as just picking the nearest color value. It's going to involve some linear interpolation by definition, right? So let's take a look at these four texel values only. So I isolated these 4 texel values, and I'm going to blow it up just a little bit just to give us some space. All right, so I am interested in this region between these four textile positions. Remember, I was putting them at the centers of my textiles, but now I'm connecting them to form this region in between four texture samples. And if my point is in between these four texture sample positions, I'm going to be using these four textiles to compute the value exactly at this point. All right, so let's do that. I'm gonna start by naming my color values. Let's call them C0, C1, C2, C3. Color values defined at these texture samples or textiles. And the color that I would like to compute is, let's say it's going to be C. Bilinear interpolation is fairly simple. I'm going to have to do a number of linear interpolations. I'm going to have to do linear interpolations in 2 dimensions. Now let's take a look at this dimension first. You can think of this as like the X dimension or U dimension, if you will. All right. In U dimension, let's say that the distance between this vertical line and this point C is S. Now, if this is 1 unit in number of pixels, it's just 1 unit, right? And if this distance is S units, then the remaining distance is going to be 1 minus S. So I can use this to linearly interpolate my colors C0 and C1. And if I were to interpolate C0 and C1 and find the corresponding value over here, right underneath this C, just vertically underneath, that's going to be, I'm going to call this C01. And I can do a linear interpolation to find the value there using this simple linear interpolation formula. C01 is equal to 1 minus S times C0 plus S times C1. Simple enough, right? We've done linear interpolation. We can do that fairly easy. Now, I'm going to do the very same thing for the 2 colors above here as well. And when I do that, I'm going to call it C23 because it's interpolating C2 and C3. Same function, it's just interpolating C2 and C3. Simple enough? All right, so we're done with our interpolation in this U dimension. Now we're going to look at the V dimension. And the nice thing here is that now I have 3 color samples, 3 positions here. Like I know the color over here. I know the color over there. I want to know the color in between here. So I just need to look in this dimension, right? Fairly easy. Let's say that, this distance is T. And so the distance above it is going to be 1 minus T. I can just do a linear interpolation of these 2 values and I get my answer, right? So, bilinear filtering. Doing filtering in 2 dimensions. One of them, I first do linear interpolations, 2 linear interpolations in 1 dimension, and follow it by another linear interpolation in another dimension. But you don't have to. And the thing is, this is sort of interchangeable. I could first do linear interpolation in this dimension, and then do linear interpolation in the other dimension. I would get exactly the same thing. In fact, in a lot of cases, this is implemented as just one bilinear interpolation. That is, I'm just going to take these 3 equations and combine them together. Are you ready? You can just combine these together by expanding these C01 and C23. And if I do that, I get this function. Right, it's just I just expanded it. It's exactly the same thing. So yeah, this is the bilinear interpolation, and I can easily, interpolate these 4 color values like this. Now, here's something geometrically interesting. At least I find it interesting. So if you take a look at it here, you see that there are 4 color values and 4 weights associated with 4 color values. So if you look at the weight for C0, that's going to be 1 minus T times 1 minus S. 1 minus T times 1 minus S is the area of this region over here, right? So the area of this region is the weight of this color value. Same goes for all the others, like the area of, let's say, this region is going to correspond to this color value, right? And area of this region is going to be this the weight for this color value. I kind of like it. It's geometrically interesting. Right. Simple enough, right? Not too difficult, just a bunch of linear interpolations, basically, or you expand it and write it in one bilinear interpolation. Does it improve things, though? What would it look like if I were to compare this to nearest filtering? Bilinear filtering versus nearest filtering. I'm going to show this on my face. Are you ready? There it is. So this is nearest filtering, and this is bilinear filtering. All right, so over here, I can distinctly see each one of my texels as little squares. Over here, they're kind of more hidden. I'm sort of interpolating between them, and things are looking more smooth. And are they looking smooth? Definitely more smooth. Can you see the pixels over here? Okay, texels, can you see them? I mean, over here you can obviously see them, like they appear like little squares. Over here, yeah, these two images are exactly the same resolution. I'm just doing bilinear interpolation here to find the color values in between. Can you sort of see the resolution of this texture here? Kind of, maybe. Can you see the size of a texel? Like over here, you can see the size of a texel, right? There's a little squares. Over here, they're kind of hidden. It's not as obvious. But if you pay close attention, you can actually see them. Like, for example, how do I show this to you? I'm talking about like over this region, near the beer, like there's some sort of bright areas. You can kind of see like there are like some vertical and horizontal shapes that form that you can recognize, right? So it's not perfect. Definitely better than this, but not quite perfect. And this is not necessarily the best we can do with this. We can actually do something a lot better. A lot of times when people talk about texture filtering, they talk about nearest filtering and bilinear filtering, but there is stuff that we can do here, that we can actually do things that are better than bilinear filtering. So for nearest filtering, all I did was I looked at this one value that was closest to it. For bilinear filtering, I look at the four closest values. So if I wanna get better, I just need more information. And the reason why, so these texels are still somewhat visible here. They're not completely hidden from me. Is because as this point moves out of this range of 4 pixels and moves over here, I'm going to be using a different set of four color values for texels. And my texture filtering is not continuous across this direction. As I go from this point towards this point, there is some continuity. That it's not completely discontinuous like the nearest filtering. But the change of color shifts. So color is sort of going towards one color and then it abruptly starts moving on to another color. And we can actually detect this. Our eyes are good enough, and then the processing that goes on in our heads, it's good enough to detect this sudden change in the way that the color gradient is moving. So it's moving in one way, the color is going to, the color is moving towards a color, and then it abruptly shifts and starts moving towards another color. And we can see this, we can recognize this as like an edge, like a vertical and horizontal edge. And if we want to do something better than this, we kind of need to make sure that the color changes more smoothly, right? So we need at least C1 or C2 continuity. So this is going to give us no continuity. This is just going to give us C0 continuity if you want to be more specific. So we need to have at least C1 or perhaps C2. So I can do something better than bilinear. That would be bicubic. Now bicubic is going to look at not just the 4 closest values, but it's going to look at all texture values in a 4x4 neighborhood. And it's going to do a weighted average of these such that the texture, the color gradient here as I move from one position to another is also continuous. So I'm smoothly changing colors from one position to another. Now, if you look at this bicubic example here, you shouldn't be able to see any easily detectable horizontal or vertical lines, right? So they're sort of, I mean, it's still blurry. Yeah, I'm still using the same amount of information. It's still a very low resolution image, all right? I'm not doing anything. I'm not adding more information here. I'm still using the same information. I'm just using it a little better. So I'm hiding where the texels are just a little bit better by using bicubic interpolation. So can we do better than bicubic? I mean, I could keep increasing the function smoothness, but it won't really help. But this is smooth enough, all right? Extra level of smoothness is not going to help. So what can help is doing something like this, right? So from this image, if I could construct something that has more data in it, and this sort of filtering is called science fiction, right? So this only happens in movies when you say, can you clear this area? It's just zoom in and all of a sudden there's more information in there. Yeah, so this doesn't exist. I'm sorry to tell you. I mean, this sort of requires adding more information. Now, there are ways to add more information. Yeah, there are ways, but I mean, I simply do not have this information in my texture, right? I'm not gonna get this. I kind of need to figure out a way to add information, and there are sort of maybe ways to do that, but that's going to be, I kind of need to hallucinate extra data. And if I have some extra data and somehow my extra data fits here, there are things I can do, but no, I won't be able to reconstruct this image perfectly. There's absolutely no way, right? I can only hallucinate this image by sort of imagining, well, I guess it looks something like this, maybe. And that's about it. And yeah, there are some machine learning methods that could be applied here that could hallucinate an image, but would it actually reconstruct the original image? No, it would. Yeah, no way. It will do something. So there is no way to do this. The only way to do this is to have a high resolution image as my texture to begin with. All right. So if I use, let's say, bilinear filtering and put this texture on my teapot, and somehow I don't like it, and somehow it looks too blurry to me, and I want to do something better, I just need to use a high resolution texture, right? I just need to use a texture that has more texels, more information in it, right? So this is what we do, right? You never want to see this on a high quality model, right? So when you have a high quality rendering of an object, you actually want to see all the, you won't be able, you shouldn't be seeing the texels in any way. Texels should be small. Texels should be very, very small, so that you can't really tell. They should be on the order of, in size wise, in screen space, they should be about a pixel or even smaller, right? So ideally, that's what they should be. Okay, so this is what I want. I want a high resolution texture on my teapot. Good. What's the problem? Here's the problem. I picked this resolution and I was very happy with it. Let's say, not that this is a great texture, but whatever. Let's say I'm happy with it. What happens if I move this teapot far, far away? What happened now? Well, it's it's gone too far. So now my texture is a little too high resolution, right? I mean, I really don't need that high resolution texture here. I could get away with a lower resolution texture in this case, but I did use a high resolution texture so that if this object ever comes close to the camera, I'm not going to have problems. But when the object is moving away from the camera, then I just have, alright, I have unnecessary amount of data in my texture. Okay, I mean, why would I care? It's okay, right? I have enough memory on my computer, on my GPU, whatever I'm using for rendering, it's good enough. It's fine. Or is it fine? Sure, it's fine. See, like, it's looking okay. It's looking okay because this is not bilinear filtering. If I do bilinear filtering here, are you ready? If I do actual bilinear filtering here, this is what it will look like. Lovely, isn't it? What is happening? Can you see this flickering? I hope you can see this flickering with the video compression. Video compressions are pretty good at filtering out everything, but this is sort of hard to get rid of. So, you know, like my texture is sort of dancing in the background, right? I mean, over here, closer to the camera, things are okay. And things are okay because my texels, the size of my texels are on the order of a pixel. But as you look away here, as my texels become very, very small as compared to the size of a pixel, and I start getting this funny thing. So what's going on here? Let's talk about it. So let's say this is my texture and I'm putting this texture on a plane, all right? And I'm going to render an image of this using my lovely camera here. So I've just positioned my camera over here and this is the image. This is the image that I'm rendering. Good. Okay. Now, just to illustrate this, let's render a very low resolution image. Just to illustrate what's going on. Otherwise, the pixels are going to be too small and I won't be able to show you anything, right? So low resolution image, they're giant pixels here. So what's going on here? When I'm rendering this, I am going to compute the color values at the centers of these pixels, right? Because my fragment shader is going to generate the texture coordinates at the centers of these pixels. So basically, I'm going to be looking at the texture values that correspond to these points. And that's what I'm going to be using. So let's pick one of these pixels here. I just picked this one, right? So this one pixel, let's concentrate on this. If you look at the center of this pixel, it corresponds to a particular position on the texture, and the color value at that point happens to be this. And that would be the color of my pixel, right? I'm doing bilinear filtering. I'm even doing bicubic filtering, whatever. I just did a very nice filtering. I picked this color value at that point very precisely, very nicely. I got this and then I painted my entire pixel with this because what is painting a pixel? It's just picking one color value. Alright, so this is my pixel. But if I take this object and just move it slightly, all of a sudden that point at the center corresponds to a different color. Now my pixel has a different color. So if I were to move my object back and forth, I'm going to be getting one color after another color, one color after another color, right? So this is the lovely flickering that we've been seeing. And it's very annoying, right? We cannot possibly accept that. We kind of need to figure out a way to get rid of this. Now, what we should be doing, actually, is not picking one or the other. We need to pick a color that is representative of the entire texture that corresponds to that pixel. So we need to pick a color that's in between the two of them, not either one of them. And such that that color would be a good representative of this portion of my surface that I'm seeing. That's what I want. That's what I would like to get with my desired filtering, whatever that is. So this portion of my texture, the average color of this portion of this texture, whatever that color is, that's what I want to get out of my texture filtering. Now here's the practical problem here, guys. Practical problem. My texture here, I want a high quality image, right? So this could be a very high resolution image, my texture. And this lovely area that corresponds to 1 pixel, that can be arbitrarily large. It can be very, very large. It can cover the entire entire texture image. This pixel can cover the entire texture image. How? If my object is moving away from the camera, and now my object is 1 pixel wide, and that object will have a color on it that will require me to look at all of my pixels and compute an average. Well, if you haven't guessed it already, that's very expensive. I mean, you can do this in finite amount of time, but it's going to require you to read the entire texture and take the average of this, and that's a very expensive operation. Especially if you're trying to do interactive rendering, that's going to be way too expensive. And even if you know you could live with that, you know, even if the pixel area is not that large, it's still going to be relatively expensive, right? Even if I look at a 10 by 10 area, I'm averaging 100 values instead of 4. 4 would be just bilinear filtering. So that's going to be expensive, and I don't want to pay the cost of this because I'm not going to be doing one time. You could say, oh, pixels are small. I mean, most pixels are not going to cover the entire image, but guess what? I have a lot of pixels. If I do this computation for all of my pixels are small because I have a lot of them. So they add up, right? My rendering is going to take forever if I keep doing that. So I need to figure out a way to make this fast. I need to figure out a way to either compute this color value or at least approximate this color value. But I need to do this fast. So the solution is what we call pre-filtering. So I'm going to do some filtering operation before I render that will make it easier for me to compute this color efficiently and quickly. All right. So there are different ways of doing pre-filtering. There isn't just one way, but the way that's by far the most popular method in computer graphics by far for doing this type of pre-filtering is Mipmapping. So here's how Mipmapping works. With Mipmaps, I'm gonna have my image. Let's say this is my original image with its original intended resolution. This is a high resolution image that I want to use as my texture. I'm going to call this my Mipmap level 0. All right, this is my high resolution image. And starting with this high resolution image, I am going to generate a number of low resolution images, right? So this is going to be my level 0. And from level 0, I'm going to generate level 1. And then from level 1, I'm going to generate level 2. And then level 3. And then level 4. And 5. And 6. And then finally, let's say level 7. So I started with my original image with the desired resolution. And from that, I added 7 Mipmap levels in this case. Now, if you pay attention here, you should see that if you compare the resolution of a Mipmap level to the previous resolution, every time it's like half the resolution, right? In either direction. And so if my texture resolution is a power of 2, if my original resolution level 0 is a power of 2, then every 4 pixels in a lower level will correspond to 1 pixel in a higher level. So every 4, I average the 4, I get a higher level texture. And same goes for, all of the levels. So every 2 by 2 region of a pixel is converted to a single pixel value for the higher level. So this is the pre-filtering operation that we do for generating what we call Mipmap levels, right? So what this allows me to do is that starting with my high resolution image, level 0, I generated lower resolution versions of the same texture. Now, I said if my texture is a power of 2, texture resolution is a power of 2, back in the day this was sort of like a hard constraint, like we we required all textures to have resolutions of powers of 2. It's not like that in today's graphics. There are ways to compute mipmap levels for any resolution image. It just becomes a bit more messy. But if it's a power of 2, then we have this nice structure, right? Every 4 texels correspond to 1 texel in the higher level. If it's not exactly power of 2, the computation is going to be a bit more messy. But it is still possible, right? So mipmaps are not limited to powers of 2 only. It's just the idea is that we get lower and lower resolution versions of our original image. So here's how I'm going to use this. So this is my pre-filtering operation, and I have these pre-filtered images, and I'm going to use these pre-filtered images at render time. And here's how. So this is the area, remember, that I would like to sort of approximate the color. Using mipmaps, what I'm going to do is I'm going to draw a box. I'm going to draw a square that will encapsulate this region that I'm interested in. It can be approximate. It's not too important. So I have this box that sort of corresponds to this area. So instead of computing the color that corresponds to this funny region of the pixel shape on this texture, I am going to approximate it as the color of this region that sort of encapsulates it. All right? I mean, it's definitely going to be much better than just picking one color value at the center. So it's going to be approximate is what I'm trying to say. So, all right, if this is the case, then what I need to do here is just pick a mipmap level that corresponds to pixels of this size. So remember, if my texel size was on the order of a pixel size, on screen space, then things were okay, right? I wasn't getting any problems. So if I just pick a low resolution image, low resolution texture, such that the size of its texels are sort of close to the size of this projected area of a pixel, then my filtering should be okay. So I can just use bilinear filtering and I'll be fine. So here's what I do. I just pick that level, pick that mipmap level, and then I do bilinear filtering here. Good enough? Almost good enough. The trouble here is that, remember, we have mipmap levels are generated such that every resolution is like half the resolution of the previous one. And this is the case because if you do that, things become very, very efficient, because I have my high resolution image, my level 0. My level 1 is going to have 1/4 of the pixels in it, right? My level 2 is going to have 1/4 of the pixels and of that, right? So like my successive mipmap levels will take less and less and less storage as compared to my original image. So I don't really spend too much memory, it's extra storage to store my mipmap levels. But because of that, the jump of texel size between mipmap levels is not something I should ignore. So, I have this size. If I go to one higher resolution image, I'm going to have half the size. Now that one is going to be too small, and this one is a little too big, if you pay attention, right? This is a little too big, and the other one would be too small. What I would like is some level in between them, but I don't have that. I only have those levels. So what do? So to compute the color at this point, I'm just going to compute it at this level, right? And I'm also going to compute this. Whoa, nope, wrong direction. Go back. All right. I'm also going to compute this at this level. And I don't have to choose one or the other. I can just combine the two. So first, I'm going to do a bilinear filtering with one of the levels. And then I'm going to do another bilinear filtering with the other level. And then, depending on the actual size of this area that I picked, I'm going to interpolate the color I computed here and the color I computed there. I'm just going to do a linear interpolation based on the size that I actually wanted. All right. So this is going to be my best approximation of the area, the average color that corresponds to that pixel area. And this is what we call trilinear filtering. So it's a bilinear filtering, and you add another linear interpolation in between, that becomes trilinear filtering. That's what we call it. So sometimes we call it mipmap filtering, sometimes we call it trilinear filtering. Although you can use mipmaps without having to do trilinear filtering. You can just skip this last bit if you can just use one or the other level, but you won't get the same quality. All right, so let's take a look at what this would look like. So here's a checkerboard texture applied on a plane. If I just use bilinear filtering, I get things that are not very good. Yeah, like I had flickering in an animation, but even in a single frame, you could start seeing some patterns here, over here, that actually don't exist in the texture, right? Texture is just this checkerboard. But I am getting this funny thing because of the way, well, that's what we call aliasing. But we'll talk about aliasing later. Basically, I'm getting visuals that don't actually exist in my scene definition in this texture. If I use mipmaps with trilinear filtering, I'm gonna get something a lot better. Ready? So much better. So much better, right? So I sort of got rid of all this stuff, and I'm just putting the average color back here. Things are so much better, right? So much better. Not great, but definitely better. But not so great. Not so great. All right, let's see if we can do this better. Like here's the thing. If you look at like the pixels, there's the pixels all the way back here. They're kind of a little too blurry, right? They're just gray. It just became gray. It doesn't look very realistic. It's just becoming gray. And the reason why this is happening is that, you know, if you pick a pixel like this and put it on texture space, that pixel would look like this, but for computing our mipmaps with trilinear filtering, we started by saying, hey, let's pick a box that sort of encapsulates that area. And when I did that, I sort of blurred my image a little too much. Because I just needed this sliver of a texture, but I just picked this box area. So if I could just compute this range, this shape, I would get something a lot better, right? So, and if I did that, I would get something that would be a lot less blurry and a lot, much better in terms of texture filtering. And that would be what we call anisotropic filtering. And anisotropic filtering is tricky to implement, but it's conceptually very, very easy. All you do is instead of doing trilinear filtering one time, we're going to do trilinear filtering multiple times, like so. So in this case, I have 3 trilinear filters. So with 3 filters, I sort of created and I sort of sampled an area that is closer to the actual area that I'm trying to sample. So I get a much better approximation of the color value. And if you were to compare these 3 different options, as you can see, bilinear filtering is not great. Mipmaps are, they're much better, but still they sort of blur a little too much. And anisotropic filtering is going to get rid of that extra blur. And anisotropic filtering is actually particularly important in cases like this. It's like when you have a plane that is becoming almost surface normal, becoming almost perpendicular to your view. So it's just something that's going off in the distance. Now, when that happens, your pixel area in the texture space becomes so elongated. And when it's so elongated, mipmaps would just overblur. Trilinear filtering will overblur, and you will need anisotropic filtering to minimize that blur. Minimize that overblur, right? But it's going to be expensive. I'm going to be cheap because I'm doing multiple trilinear filterings now instead of doing just one trilinear filtering. So it's, yeah, anisotropic filtering is expensive because of that. But it provides much better results. Right. Okay, so this was a nightmare. I didn't call it nightmare, but this was what I was talking about when I say our troubles just began. Texture filtering was the difficult part, and as you see, there's this so much involved. Now, the good news here is that this is a very fundamental operation in computer graphics. So our GPUs come with dedicated hardware to do this filtering for us. So for GPU, I'm going to say, hey GPU, this is my texture, and just do anisotropic filtering with mipmaps on this, and GPU will do that for you. So that filtering part, when you're doing real-time rendering, is not something that you're going to have to implement by hand. At the same time, not implementing it is easy, but also it's GPU has this hardware units that do this for us. And because they have specific hardware units to do this, they can do this very, very efficiently. So by some estimates, what the GPU hardware can do for texture filtering is about 10 times faster than a software implementation that runs on the GPU. So that these hardware support for texture filtering is actually very, very valuable. It's a very, very crucial component of having high quality, fast rendering that we have on our existing GPUs. It's a very, very important component of that. All right. So this was all about texture filtering. Now I want to step back and talk about textures in a slightly more general way. Now, textures can be all sorts of things. Now they could be used for all sorts of purposes. We'll get to that. They could be defined for all sorts of different objects. We'll get to that. But I want to say that there are different ways of storing textures for surfaces, even just for what we've been trying to do. Of course, yeah, there could be raster images. That's one thing. And raster images, you expect them to be 2D, but I can also just take one raw raster image that would be a 1D texture, or I could just extend it in another dimension. It could be 3D, higher dimensions, whatever. Some sort of raster image of some dimension. I probably shouldn't call it an image when it's higher or lower than 2D, but whatever, you get the idea. But they could also be procedural. What do I mean by this? I'll talk about this a little bit next time. Any kind of function that you think about could be a texture. Just write some function, it does something, that could be a texture, it could be some algorithm, it could be some mathematical formulation. And I can call it a texture. I don't have to necessarily store texels, right? I can just compute the texture value on the fly if I want to. That's another way of representing textures. But beyond these, like just for representing specific texel values, there are alternative structures than just these raster images. Now remember that we're trying to put these textures on surfaces, and there are structures. What we typically do is we take an image and put it on a surface. But as I hinted early on, maybe a little more than hinted early on, is defining this mapping between the texture space and object space. Defining this mapping was a very messy process. Now I can spend an entire lecture on this easily. Actually, I could even maybe spend an entire course on this easily. I'm not going to do that. I'm just going to spend about 5 minutes. But let me tell you just a few things. Just defining this thing is very labor intensive, very, very expensive because it requires a lot of manual intervention. And at the end of the day, you get textures that have all sorts of problems when you're rendering. You actually get some visual artifacts, which I'm not going to show. I'm just going to tell you that you're getting all sorts of visual artifacts out of them as well. And that's creating all sorts of issues. Even though this is a very popular way of defining textures and storing textures, it's not ideal at all. And at least one of you guys was asking if there's a better way than this, and yes, there is. There are alternative structures. I actually gave a course on this with Marco Torini and Sylvain Lefebvre. We at SIGGRAPH 2017, we call this Rethinking Texture Mapping. There are a whole bunch of methods out there that do a better job in many ways than our regular old texture mapping. From those, I'm going to tell you two of them. A popular one that's called PTEX that came out of Disney Animation Studios. So PTEX is a very brilliant and simple idea. Instead of trying to define a mapping for this entire model, why not take each one of my low resolution quads, like quads defined on my low resolution image, and put a separate texture on it? That's a simple mapping, right? Take each face and put a texture on it. And that solves one of the biggest problems of texture mapping, that is defining this mapping. So with this sort of a structure, as soon as I have a quad dominant mesh, which is what I typically use for modeling anything, right? As soon as I have a quad dominant mesh, I have my mapping implicitly defined for me. I don't need to define a mapping because I'm going to take each quad and I'm just going to plop a texture on it and I'm done, right? So I don't need any manual defining mapping or anything, nothing complicated. And so this became very, very popular in production because people didn't have to worry about this mapping. At the same time though, I came up with my method. This was, and I called it mesh colors. So that does pretty much the same thing, just slightly differently. That slight difference actually makes an important difference in practice. What mesh colors do is that they define the colors, the texture sample positions directly on the polygonal mesh surface. So if I have, let's say, a triangle like this, I can define mesh colors with whatever resolution that I want. With mesh colors, I'm going to have exactly color values exactly at the vertices and along the edges, as well as on the faces. And I could have triangles or quads. So I can define colors this way. And with this sort of storage, this doesn't require anything other than just storing the texels. Okay, of course, the resolution and whatever. It takes a little bit of information, but it definitely does not require as much information as you would need for storing regular 2D texture mapping. It actually stores less information, and it solves all of the problems of texture mapping. It actually solves the problems of PTEX as well when it comes to rendering. So this also eliminates all the rendering related artifacts, which I'm not going to get into that. Don't get me started on that. That would take me a long time. So yeah, it solves all these problems. And the good news is that actually with current GPUs, it's possible to implement a version of this sort of texture filtering or this sort of texture representation on existing GPUs. Not exactly. I have a relatively recent paper on that with my student Ian Millett and my collaborator Larry Seiler. So we talked about how to extend existing GPUs so that we can easily do mesh color filtering on the GPU. So, but existing GPUs actually support a part of this already. Not all of it, but most of it, I would say. The most important part is already supported. So yeah, there's a better way of doing this, and probably we'll move along in this direction. So as we're talking about textures, I want to talk about textures and texture mapping because that's still the standard today. But I had to mention this to you guys because, hey, well, it would be embarrassing if I didn't teach you this as my students. I'm telling the entire graphics world that this is what we're supposed to be using. So if I don't tell you guys this, that would be really embarrassing. So I didn't want to do that. Yeah, so, but still, you still need to know texture mapping, and we will still implement texture mapping as a part of our project, but you should know that something like this also exists. Alright, I'll just leave it at that. And this is what I plan to talk about today. Next time, in our next lecture, I am planning to go over how to use textures on the GPU. That's going to be some specific WebGL instructions that we will be using for storing and accessing textures. It's going to be slightly complicated, but not really too complicated. Once you understand how this thing works, it's not that complicated because GPU will do the actual difficult part for us. It will do the texture coordinate interpolation automatically, and then it will do a texture filtering for us. So all we need to do is to tell GPU, hey, this is my texture, just use it. That will be the topic of our next lecture. And after that, I believe you will have enough information to finish the remainder of our upcoming project. So I'm gonna end it here, and I'm gonna see you all next time.